All right, we're doing a quick test review right now for everything for tomorrow's test. This is going to cover essentially everything with a graphing unit of quadratics. The first skill that I want to talk about for tomorrow's test is characteristics. We have to remember the characteristics from the video that I made for our quiz prep, okay? Specific characteristics that we need to be able to identify from a graph is the vertex, the axis of symmetry, a max or a minimum value, the domain, the range, where it's increasing, where it is decreasing, and what the intercepts are, all right? As well as the positive or the negative region, all right? So first, we have a graph. The obvious point that I think we should all be able to identify first is our vertex, and that's just counting our x value, which is over there at 1, comma, down to our y value over here at -4. Okay, so 1, comma, -4 being our vertex. Now, one of the things we've talked about is that our axis of symmetry cuts through our vertex perfectly as a vertical line. Axis of symmetries being a vertical line. Vertical lines are written as x equals that exact value of our vertex. All right, so x equals that value of the vertex. X equals 1 in this case. Now, because this function opens upward, all right, because this function opens upward, we know that the point here at the bottom, this vertex, yields a minimum height. So we have no maximum. We can just put none there, and our minimum is a height of -4. All right, so our minimum being a height of -4. Our vertex yields either a maximum height or a minimum height. It is also where our range begins, okay, or ends. If you think about it, our range always goes bottom to top of our function. So in this case, the bottom of this function is right there at that height of -4. We have a bracket around that because we have a point that exists there, and we go all the way upwards to infinity, all right? Our domain for all of these, if you recall, any quadratic function has the domain of all real numbers. Essentially, that just means you can plug in any x value that you want to into this function, and it will yield an output value specifically. So we have all real numbers, which we signify using interval notation as -infinity to infinity. Okay, so now, the other main thing that we need to talk about from our axis of symmetry is our axis of symmetry separates and changes directions, if you think about it. When we did our word problem where someone throws a ball up in the air and then it falls down, that vertex signifies a location where it changes directions from either going up to now it's going down, or in this case, going down first, right? This is going down first, and then it changes directions at that x location. Now, I want to talk through our intervals. Our increasing and decreasing intervals, we're looking at x value intervals. Same thing when we talk about positive and negative intervals. We are just looking at x value intervals, okay? So I want to highlight that main point, and we are going to get back to these two. Let me just kind of clean up this board a little bit after we go through maybe our intercepts, okay? So for example, our y-intercept, that is just a counting idea. And our y-intercept is where does it cross the y-axis. So that line right there that I just signified is the y-axis, all right? And we're looking at where our function crosses it. So the point on that is a coordinate. 0 is going to be our x value for that, and then in this case, -3. Now in this case, we also have two x-intercepts. Okay, so we have two x-intercepts. And so we're going to list both of those points. Notice they cross the x-axis. And so they have a height of 0. So each of our points, we already know the coordinate for y is going to be 0. All right? And we're just counting. That's a -1, 0, and that's 3, 0. All right, I'm going to pause this right there. All right, getting back to the two final characteristics I want to talk through our increasing and decreasing intervals or our positive and negative intervals. I want to highlight this again, and you can press pause if you need to at home anytime. We just kind of stopped class for a little bit for me to go over and explain this to the students that are here. But specifically, we want to make sure that these intervals, we are just thinking of x values. So once again, our function is going down, all right? Then at this x location of the axis of symmetry, it's going to change directions, and then it's going to start to go up again. So this is clearly our increasing region on the right, and this is our decreasing interval on the left, all right? And we're just looking at x values for this region, meaning we start time all the way over here on the furthest x value or concept over there at negative infinity. And along this x-axis, starting all the way over here at negative infinity, our graph is going to be really high. But we're looking at x value of negative infinity, very high y value, but it's going down over time. And it continues to go down over time until we get to this middle x value, which we've already said is 1. Okay? So that decreasing region happens between the x locations of negative infinity and 1. I actually explained increasing and decreasing in my previous video on the quiz review, so you're welcome to go back and look at that. I think it'll help you a lot. I'm going to kind of breeze through this fairly quickly right now. Okay? Then, now that we get to this x location of 1, all the way for the rest of time on our x-axis, all the way out to infinity, not up to infinity, but out to infinity, for every x value between 1 and the x value of infinity, our function goes up. Now, it starts here and it goes way, way high, but that's not what we care about. We don't care about how high are we going. We care about over what x values do we happen to be going upward. So over the x values from 1 to infinity. Okay, and so that would be our increasing region. Okay. The final thing we want to look at now is going to be our positive and negative intervals. Okay, so I'm just going to use a highlighter to track that. So our positive, I'm going to use blue for positive, okay? Our positive intervals are above the x-axis. We'll use yellow for negative. Our negative values are below the x-axis. And these are just heights. These are positive heights, these are negative heights. But our answer, once again, is just going to deal with x values. So these are positive heights, negative heights. And once again, this is a major review topic item from content from semester 1. Right? We dealt with positive and negative intervals all throughout semester 1. We've also dealt with it a little bit previously this semester. And we're just kind of adding this in and making sure that we understand it. The only x values we care about now are the beginning of time, the x-intercept, the next x-intercept, because those are the moments where it crosses the x-axis, right? If you notice the beginning of time all the way to this x-intercept, over these x values, we have this positive shaded region. Right? So we have a positive region from the beginning of time, negative infinity, to that negative 1. We're actually going to pick up with another positive region later. But now let's talk about what happens between negative 1 and 3. So over the x values of negative 1 to 3, we happen to have negative heights. And so our negative heights happen between these x locations. You can think of these x locations as moments in time. Okay? So we've got moments in time, x values, between negative 1 and 3, just so happens to have negative heights. Then we pick back up again, moments in time after 3, and for all rest of time to infinity, we have positive heights again. So from 3 to infinity would be my second region there that are positive. So we're going to actually have 2 positive regions here. So this covers a full summary of every possible characteristic that we could have on tomorrow's test. I actually want to bring this great question up that one of my students just asked me. We kind of stop and start as we go here. They asked, is it always going to be 2 positive regions? And I said, well, what if we flip the graph upside down? So let me actually redraw the whole thing. So if we have a reflection, notice now there would be 2 negative regions. This would be a negative region, and that would be a negative region. So we'd have two negative regions then between those x-intercepts. We could also, side note, if I draw this a couple other ways, okay, we could have a function that's only ever above the x-axis. This means it would only ever be a positive region. Okay, this is a special circumstance case, but it is good for us to understand. This would mean all real numbers are positive. It never is negative. Or if we reflected that, oh, also this means no x-intercepts. Also, if we reflected it fully down and was below the graph, still no x-intercepts, only ever a negative region. So really good questions there. We could also be asked for the characteristics if given a function. Okay, so if given a function's equation, we could be asked for the characteristics. Now, I'll probably just pause this and ask my class this and fill you in on the answer for a second. But I want to make sure that we understand there's a simple thing that we do every time we're given the equation of one of these quadratics. All right? Okay, love my students. We just asked the question, what is really the essential only things we truly care most about when we are identifying what to do next if given a quadratic equation function, okay? We want to find the a value. That is always going to be very obvious and apparent no matter what form we're in. Here we're in standard form, but when we get later to the review of intercept form or quadratic, or vertex form, the a value is always going to just be like hitting us right in the face. It's going to be staring us right there as it's a part of our equation. Okay, so the a value is important. Second thing we want to talk always about is the vertex, which is what one of my students called out. Okay, if we can identify our vertex, everything else is kind of built off of that. In fact, given the a value and the vertex, we can graph our function, and we can also identify all the transformations from it. Okay, so if you're wondering what to do specifically in standard form to find the vertex, we are going to identify our a value, our b value, and our c value in standard form, and we're just going to calculate negative b over 2a. So if I do a little bit of work over here on the side, I'm going to notice negative of b, which is already negative 6. So I'm negating a negative. It's going to turn into a positive. All divided by 2 times whatever our a value was, which we just identified was 3. Okay, this is just going to go in as the x portion, the x coordinate of our vertex. All right, so here I've got the negative of negative 6. I've got positive 6 divided by positive 6, and I just get the x value of 1. So, boom. We're going to take this x value of 1, and we are going to plug it in to our standard form equation. All right, I'm going to plug it in not for a, b, and c, but for x, which is squared here, and x, which is linear here. So I've got 3 times 1 squared minus 6 times 1 plus 2. Okay, students out there, give me a thumbs up that we're already calculating that. Okay, we got 3 minus 6 plus 2 is negative 1. Okay, so our biggest goal when we're dealing with a standard form is to find the vertex. Once we find that vertex, everything else stems from there. First off, that already answers one of the main characteristics that we're going to be looking for. That characteristic here being identifying the vertex. Second thing we want to know is maybe a rough shape of what this function looks like, because the a value is going to help us identify if it opens upwards or downwards. In this case, 1, negative 1, opening up upwards, fairly steep. I'm just doing a rough sketch of it because that's going to give us a great visual of what's going on. Now we know our main 3 x values, like we just went over, are 1, negative infinity, and positive infinity. Right? Those are the main moments in time. The beginning of time, the time in which our function changes direction, and then the end of time. So the beginning of time, till it changes direction, it is decreasing. So beginning of time till our axis of symmetry. Then it changes direction, and from our axis of symmetry till the end of time, it is increasing. The vertex also helps us identify the range because we can identify here it's a minimum again, okay? And since it's a minimum that we actually exist at, that height, it's a y value of our vertex, -1 all the way up forever. So we've already done this from a graph. We're doing it from an equation now. I'm just reminding you it's best to sketch a graph as your best manner to get a visual for what's going on, okay? And again, the two ideas that we set are what? What do we need to find if we want to sketch a graph? Yeah, vertex and the a value. Very good. Okay. Y-intercept is going to be the final thing I want to talk through. Now, clearly, my graph doesn't look beautiful for my y-intercept right here, right? I just did a rough sketch. I don't even know where it's going, okay? But I don't need my graph to identify the y-intercept because if you recall, the y-intercept is always the location when our x value is 0 because that's where it crosses the y-axis. So if our x value is 0, this term dissipates and goes away. Not dissipates, it nullifies because it gets a value of 0. This term also nullifies because it gets a value of 0. And we're just left with this as our y value of our y-intercept. More on that later when we do the word problems, because if you recall, that was where we plug in our initial height, which represents our y-intercept. Okay? All right, the next main skill that we want to talk through for the test tomorrow is transformations, and specifically being able to identify them from a graph. Because A, if we know how to graph it, which we've spent so much time practicing, then we should be able to get to this step. And since we're already at this step, we're assuming, let's talk through how to identify our transformations from a graph. So the only two things we care about are the a value and the vertex. And this is kind of the core common theme that I've been using to teach this for the last week or so. Once we know our a value and our vertex, everything stems from that. If you recall, the normal parent function is graphed at the vertex, opening upwards, looking like this. All right? Clearly, our function has changed a lot. First, it has reflected. That's found in a negative a value. So we have a reflection here. That is found with this being a negative a value opening downward. Okay? The other thing that the a value tells us is if the steepness has changed, has it stretched, has it condensed, that's called a vertical shrink. Okay? In this case, we look at the fact that as I go out 1 in each direction, it actually goes down by 2. That is why our a value here is -2. Okay? Using that pattern that we taught, and I put in the last video that we did, using that pattern to find our a values and to graph using our a values, out 1, down 2 is an a value of -2. The negative is the reflection. And our stretches and shrinks are always the positive version of this number. The negative is taken into consideration by it being a reflection. It has nothing to do with how steep it has been stretched. Okay? So it's a stretch of that positive value of 2. All right? The other thing we're going to look at is the fact that this function has moved to the right 2, and it has gone up 1 to get to the new vertex. And so the new vertex, while it originally would have been over there, has moved over 2 to the right and up 1 visually. Then it has flipped, that's the reflection, and then it has stretched. And so notice everything we need to find is in the vertex or the a value when doing these. And those would be our 4 transformations. Final thing of note, once we know an a value and we know where the vertex is, we can write the equation of that. We're just going to put it simply in vertex form. So for example, we know this vertex is right 2 up 1. We know our initial vertex form is a times x minus h. Notice the subtraction of h is what makes it the opposite numerical concept of this right 2, and then plus k. This was all stuff we've done for the last couple weeks, so it should be a simple review. So our answer then for what is that equation? Y equals -2 times x minus 2. Notice it's to the right 2, but it visually looks like negative 2. If you think about it, it's because you have to plug in x equals positive 2 to zero this out. And there's the little nuance to why it is opposite there, and then plus 1. And so this is how we write an equation in vertex form based on the a value or the vertex. Okay, talking through transformations from an equation. Again, the only thing we care about for transformations is what is the a value and what is the vertex. If you notice here, we've got an a value of -1. The only transformation that yields is a reflection. It is not a stretch or a shrink. -1 is just a reflection. If it was +1, there would be no transformation found from the a value. Over here, our a value is +1/3, so we have a shrink vertically of 1/3. So these are the specific transformations found from our a values. Okay, here we would use our -b divided by 2a to find our vertex. Here we would use just the fact that it's vertex form to find our vertex is -5, 0, which means it has moved to the left. Oop, I'm losing my board. There we go. To the left 5. Okay, so that is the other transformation there. Here I would need to find my vertex. Okay. To calculate the vertex over here, -b over 2a is -2 divided by -2, like negative of 2 divided by double that, which is also -2. So that equals 1. I plug 1 in. Negative of 1 squared plus 2 times 1 plus 1. So -1 plus 2 plus 1 is 2. Now we know our vertex is 1, 2. And so our other transformations, we would say, are to the right 1 and up 2. This is just like the bare, skimmed down, simple process. Quick little reminder, transformations just come from the a value and the vertex. Find those and you can identify all transformations. Nice little pause moment if you want to. Next, practice finding the vertex from each form, right? Practice finding the vertex, whether it's intercept form, okay, whether it is vertex form or standard form. The a value will be in each form. I'll show you that in a second. All right, so just showing y'all the 3 forms that we have. We've got vertex form. The a value is staring us right in the face. That is a stretch of 3. We've got standard form. The a value is staring us right at the face. This is a reflection, then separately a stretch of 2. And here our a value in intercept form as well. So we have actually gone through and reviewed finding the vertex in vertex form already, but I'll do it one more time. We have already reviewed in standard form. In standard form, this is when we use -b over 2a. I want to talk now about intercept form and how to find the vertex there. All right, someone in my class asked a great question earlier of how do we find the x-intercepts from an equation. Typically, we only can do that in a very simple way without having to solve a quadratic if it's written in intercept form. That's kind of the justification for why it's called intercept form. So intercept form is called this way because from each of these binomials, we could solve them to find our x-intercepts, here being x equals -1, and solving this would give us x equals 3. That's if we had a y value of 0, because again, that would be our height. So once we have our intercepts, what you have to remember is these graphs are symmetrical. Like if I were to be the graph, it would look symmetrical, this side and this side. And so what you have to remember is this and this are symmetrical over a middle concept. And that middle concept is our axis of symmetry. Well, we already know this axis of symmetry is the x value of our vertex. So that's step 1 in finding your vertex. is find this axis of symmetry that is halfway between them. Then you have your x value that you can plug into this x and this x, okay? Now in this case, we're gonna get, I think, potentially a fraction if I do this in my head, okay? But typically, that's just because here we have a shrink. Otherwise, typically you would just plug it in and be off and away. For example, if I plug it in and multiply here, 1/3 times 1 plus 1 times 1 minus 3. That's essentially all I've done is taken this value of 1 and plugged it in for x and x. Okay, calculating that out, 1/3 times 2 times -2 is just -4/3. So now I have my vertex. In this case, not the most beautiful vertex because it's a fraction, because it was a shrink, but I just wanted to show you the math behind it, okay? And clearly, that just means it's below the axis, which makes sense that it would be very condensed or shrunk, and opening upwards since we have a positive a value. So that's kind of your freebie on that problem. I definitely watch this through a few times if you need. Okay, I want to go through kind of how our a value affects our pattern that we graph. So I'm going to make this assumption for all the graphs that we're doing right now, that the vertex is already plotted for us. And in this case, I'm going to do them all from the origin. But essentially, graphing, our goal, plot the vertex. We've already talked about finding the vertex and finding the a value. Now we're talking about plot the vertex. From there, we're just going to use our a value. Okay, and the method that I've taught, if you go back and watch the previous video, is our basic a value of 1 is no stretch, no shrink, no reflection, no transformation whatsoever. We go from our vertex out and we go up 1. Then we go out and we go up 3 again, because perfect squares grow by that pattern of 1, 3, 5, 7, 9, etc. We've talked about that a few times. And so our pattern is 1, 3, 5, 7, etc. Well, now we don't need to graph all of those, but we need to go out 1, up 1, then we go out again and up 3. So it's out 1 each time, and it's just up 1, up 3 for this basic pattern that we have. Okay, so this is up 1, up 3 is the basic parent function pattern. If a was -1, same idea, vertex there. The only difference is it's a reflection. So it is out 1, down 1, out 1 more, down 3. Okay, so this gives you what to do for these two basic a values. All right, I want to copy down now a stretch in each direction. Okay, this is going to be a stretch that opens upward, so it's just a stretch of 2. This one's going to be a stretch of 3, positive 3 that is, but it's reflected, so it's going to open downward. Okay. Once again, I'm starting with my point at the vertex. My vertex at the origin. And our goal: plot the vertex. We've done that. Use the pattern. And if you recall, my little quick hint that we did was our usual pattern is up 1, up 3, up 5. Our a value is a multiplier to that. So 2 times up 1, up 3, etc. But we don't even need to go that far, right? 2 times up 1, it just stretches. Now it's up 2. So this would have been up 2, up 6. We're just going to get away with plotting just this next point on each side for now. And we're going to notice that that a value, as we go out 1, it's going to go up 2 in this case. I don't even need to keep going. That's going to be a little bit further up on the graph, obviously. So over here, this would be out and then down 3. Okay, so an a value of -3 is down 3, down 9, etc., because it multiplies to that pattern. So down 3 for that next point. Okay. Okay, now looking at a few shrinks for a values. This is on level Algebra 1, like basic introduction topic. The only shrinks we're going to look at are 1 over a whole number or -1 over a whole number for now at this introductory level. So for example, 1/2, 1/3, 1/4, or -1/2, -1/3, -1/4. And they all have a common theme where essentially looking at this denominator, whatever that denominator is, that is how far from our vertex we go out and either up or down in that same number to get to the next whole number points. For example, An a value of 1/2 means starting at my vertex, we would go out 2 and up 2 in both directions to get that widened version of this quadratic. Whereas over here, with it being, first off, negative, it's going to go down. But with this denominator being a 3, that tells us it goes out 3 and down 3. And that's just like a pattern that happens with these type of a values. So out 3, down 3 takes us to our next whole number point in this type of shrink. All right, and that kind of covers now all of the patterns that we've kind of looked at as far as how to move from the vertex to find your next whole number points. Okay, and again, our goal is always find the vertex, find the a value. If we can do those two skills, we can do everything here. All right, so looking through the basic word problem that we've dealt with a quadratic, essentially we're dealing with some scenario where someone is standing at a height or throwing an object up starting at a height. It goes up and it comes down over time. So we're essentially measuring height over time, and there's really 3 values we care about. Okay, so the initial height is our y-intercept. That is an incredibly important value to talk through, and that is an initial height of 192. So that value is 0, 192. Now essentially from this word problem, what you need to understand is at time 0, we start at a height of 192 feet, and that is our y-intercept. That's what that represents. Then we are going to get to our vertex. Now our vertex is going to be the amount of time it takes to reach our maximum height, and then what that height is specifically. So we're going to need an equation to find this. So we'll get to that in a second. And then the third and final thing we're going to look at is going to be this point right here. Sorry, I just called coordinating this. This point right here is our x-intercept. And this is going to be at the final height of 0. Because remember, x-intercepts are something comma 0. So now we've got a height of 0, and we're calculating the time in which it takes to reach that height in 0. Basically, when does the baseball hit the ground? Okay? So we're going to need an equation. And if you recall, our typical equation is always h of t, dealing with feet and seconds, is negative 16t squared plus velocity v naught, t initial velocity, plus initial height h naught, h0. So I'm going to go ahead and substitute those in. Essentially, the only thing you need to do, since gravity is always the same coefficient, is substitute in that initial height of 64 and that initial velocity of 64 and that initial height of 192. Okay? And I'll let you pause it at home, but this is the equation that we're going to use for everything else. All right, getting back to this height measured at time equals negative 16t squared plus 64t plus 192. That's our equation. Getting back to this, our vertex, since this is standard form, is still negative b over 2a. In this case, negative 64 over negative 32, because that's the double of negative 16. Reducing that becomes positive 2. So we actually already know that our vertex takes 2 seconds for that ball to reach that maximum height. That's what we've learned so far, is the time it takes to reach that maximum height. It took 2 seconds, then it changes directions. Okay? What do we do with this? Now we plug that in for our t right there and there. So I've got negative 16 times 2 squared plus 64 times 2 plus 192. So y'all might need a calculator at home. Maybe we'll check with a student here, and hopefully we can get to this. So this is negative 16 times 4. So is that negative 64? This is 64 times 2, so that's positive 128, plus this 192. Okay, so what is that? 64 plus that is 256 maybe? Is that it? Hopefully, I'm getting a thumbs up from people. 256, boom. So now we have our vertex, 2, 256. Which essentially means it took 2 seconds to get to a maximum height of 256 feet. So far we have learned at 0 seconds, our y-intercept shows us an initial height of 192. At 2 seconds, we've now reached our maximum height of 256 feet, and now we need to find our x-intercept. That will tell us how long it takes until it hits the ground. So if we want to find our x-intercepts, we are taking our quadratic function as an equation, we're setting it equal to 0. So the first thing I did is say, I'm looking for a height when it equals 0. It's hitting the ground. It's got to have a height of 0. I'm going to take this and I'm going to factor out a GCF of negative 16. Negative 16 goes into here, here, and here, thankfully. So I factor out the negative 16. What's left behind is t squared minus 4t minus 12, a simple trinomial. I'm going to take this trinomial, we've done so much factoring, and I'm going to factor it into t minus 6 and t plus 2. And from there I solve, and if you recall, solving yields the solutions t equals positive 6 seconds or negative 2 seconds. Now, negative 2 seconds is technically a solution, but if you look, that's the imaginary concept, not imaginary, that's the non-realistic logical concept where in negative time it potentially would have crossed this x-axis again, but we're not dealing with that. We're dealing with the positive answer where it crosses at 6 seconds is when it hits the ground. All right, that's everything for the test.